For the last several videos, we've been talking about electrophilic aromatic substitution. To this point, we've just been talking about non-substituted benzene rings. What the next several videos are going to cover is what happens to these EAS reactions when we have substituents on the benzene ring. In this video, we're going to look specifically at what activating groups are, and we'll talk about more about what this is as we go on. So there are two issues that we need to consider when we have a substituent on the benzene ring and we're undergoing an electrophilic aromatic substitution reaction. So if we consider the nitration of toluene, the two things we need to consider are what effect does the substituent, in this case a methyl group, have on the rate of nitration, and we want to know specifically, is it more or less reactive? And this is referred to as deactivating and activating. If it's less reactive, if it reacts more slowly, then it's deactivating. If it's more reactive and it reacts more rapidly, then it's said to be activating. The other thing that we need to consider is what is the effect of the substituent on the regiochemistry. So are we going to add the nitro group in the ortho, meta, or para position? And this is referred to as the directing effects of the substituent. So in all of the next several videos, we're going to be considering what are the activating and deactivating effects of the substituent, and what are the directing effects of the substituent. Alright, so it turns out the methyl group is activating. Toluene, that's a benzene substituted with a methyl group, reacts 25 times faster than just a plain benzene. And so because toluene is more reactive, the methyl group is said to activate the benzene ring, or the methyl group is an activating group. The explanation for this is we know that in the mechanism of electrophilic aromatic substitution, we create this positive sigma complex. Well, the methyl group is able to donate electron density to the benzene ring via hyperconjugation. So by donating extra electrons, that stabilizes the positive sigma complex, and that makes the reaction go faster. Now, we talked about hyperconjugation some last semester, but I thought it might be useful to review it a little bit. So we first encountered hyperconjugation when we talked about carbocations. And we talked about the fact that the more substituted a carbocation is, the more stable it is. And the reason we gave for that is hyperconjugation. So we know that the carbocation has this empty p orbital. When we have neighboring carbon atoms, it is able to donate electron density from the carbon-hydrogen sigma bond into the empty p orbital. And so this is what we call hyperconjugation. And so something similar happens when we have that positive charge in the benzene ring in this sigma complex. Essentially, we have empty electron space in that benzene ring, and so if we have alkyl groups that are coming off the benzene ring, they can donate some of their electron density from the carbon-hydrogen bonds back into the benzene ring, thereby stabilizing that positive charge. So the take-home message is when we have alkyl groups on the benzene ring, they act to be activating groups by speeding up the reaction because they can stabilize the sigma complex by donating electron density. So we've talked about the first effect. Is the methyl group activating or deactivating? And as we discussed, it's activating. Then the second effect we need to consider is the directing effect. Where does the nitro group add to the benzene ring? Is it going to add in the ortho, the meta, or the para position? And it turns out the nitro group, when we have a methyl group as a substituent, is going to add in the ortho or para position. Therefore, we call the methyl group an OrthoPara director. And as you can see, we get almost all ortho and para and very little meta. So the way that we'll explain the directing effects, both in this video and in the ones that follow, is to look at the resonance structures of the sigma complex. And so what we'll typically do is consider what would the resonance structures look like if the group that we're adding, in this case the nitro group, adds in the ortho, the meta, or the para position. If we consider ortho attack, when the nitro group attacks here, we end up with a positive charge on the carbon that's attached to the methyl group. And then we can draw these other resonance structures where we move that positive charge around. If the nitro group attacks in the meta position, then we end up with a positive charge here, right here, here, and here, where the positive charge is not directly connected to the methyl group. If I move the slide up a little bit, we can see that the resonance structures for the pair attack, when the nitro group attacks down here, we end up with a positive charge here, here, and here. And so in both the ortho and the para cases, we have the positive charge on the carbon atom that's directly connected to the methyl group. And so this is much more effective at stabilizing the sigma complex due to hyperconjugation, because we can add electron density directly to that positively charged carbon atom. In the meta attack, we don't get any of this extra stabilization because the positive charge is never directly on the carbon that's going to benefit from the hyperconjugation. So because when we have ortho and para attack, we have these extra stable resonance structures due to the hyperconjugation, that means that the sigma complex is especially stable when the nitro group attacks in either the ortho or the para position, but not as stable when it attacks in the meta position. And so this explains why we get mostly ortho and para and very little meta. If we were to look at the reaction energy diagrams, because the sigma complex is stabilized when the nitro group attacks in the ortho and the para position, because it's more stable, that lowers the transition state, giving it a lower activation energy, and the reaction is faster. And so we're more quickly able to form the nitro in the ortho and the para position. The meta is formed much more slowly, and so the ortho and para products predominate. Now, one other thing that we want to consider, why do we get more ortho than we do para? And we get almost exactly twice as much ortho as we do para. Well, this really just comes down to statistics. There are 2 ortho positions and only 1 para position. So we get twice as much ortho and half as much para. Okay, now I want to consider another substituent. In this case, I want to consider a methoxy group. And this is in general true for all alkoxy groups, whether it's a methyl, ethyl, or whatever. So the first thing we want to think about is the methoxy group going to be activating or deactivating? Well, there are 2 factors that we need to consider to decide whether it's going to be activating or deactivating. And it turns out these are going to give us opposite predictions. The simplest one, I think, is induction. Right, because we have this electronegative oxygen atom, it's going to pull electrons toward it, and so it's going to be electron withdrawing towards the benzene ring. And so when we have that positive sigma complex, if we have something that's going to remove electron density, that's going to destabilize the sigma complex, and that should deactivate the ring. However, when I consider resonance, I can draw the following resonance structures because I have an allylic lone pair, so I can move the lone pair down to become a pi bond. This pi bond becomes another lone pair, and so I have these different resonance structures that I can draw for the methoxy substituted benzene ring. And you can see in these 3 resonance structures, we have a negative charge on the benzene ring. And so resonance is going to predict that the methoxy group donates electron density to the benzene ring, which should stabilize the sigma complex. So which one wins? Well, when we do the experiment, it turns out that the methoxy group in anisole activates the ring 400 times more than benzene. So the methoxy group is clearly activating. And so as it turns out, resonance is generally more important than induction, right? We said that for the methoxy group, induction should tend to destabilize the sigma complex, but by resonance, it will stabilize the sigma complex. And so generally, resonance is more important, as we can see here, right? The methoxy group is in fact activating. And this should make some sense if we consider back to the stability of bases. When we consider the importance of the different effects, resonance was more important than induction. And that's generally true here, although we will see an exception later on. Now, another interesting consequence of these activating groups, it turns out the methoxy group is so good at activating the benzene ring, we no longer need the acid catalyst. Right? Normally, if we just had a plain old benzene without a substituent, we would have needed the iron 3 bromide in order to get the electrophilic aromatic substitution and add a bromine to it. In fact, when we have this methoxy group, even without the Lewis acid catalyst, we often get poly substitution. We get bromines in both the ortho and para positions all together. All right, when we looked at the directing effects of the methyl group, we saw that it was an OrthoPara director. It turns out the methoxy group, which is also activating, is also an OrthoPara director, and it turns out this is generally the case. Activators are generally OrthoPara directors, and so we get mostly ortho and para and very little meta. Now, in the case of the methoxy group, we got more ortho than we did para because of statistics. There were twice as many ortho groups as there are para groups. In the case of a methoxy substituent, we actually get more para than ortho, and this comes down to steric effects. Right? The methyl group is relatively small, the methoxy group is relatively large, and so it just gets in the way of the nitro group being added in the ortho positions, and so it's easier for it to get into the para position. So whenever we have anything much bigger than, say, a methyl group or a halogen, we tend to get para substitution as opposed to ortho substitution, just due to steric effects. Now, to explain why the methoxy group is an OrthoPara director, we're going to look at the resonance structures of the sigma complex, just like we did for the methyl group. And so, again, these should look similar. Right? When I add the nitro group here, the positive charge in the benzene ring can end up here, or here, or here. But the other thing that can happen is we can move the lone pair from the oxygen down to form a double bond between the oxygen and the carbon. And the reason this resonance structure is so good is because in this resonance structure, all the atoms have a complete octet. Remember that when we have carbocations, the carbon atom that has the positive charge doesn't have a complete octet. And when we thought about the importance of resonance structures, the first thing we look at is, does everything have a complete octet? And so it doesn't in these three, it does in this one. So this is the most important resonance contributor. And so this is a particularly important resonance contributor to the hybrid. It's particularly stable because everything has a complete octet. We can get the same thing when we have para attack, but when we have meta attack, there's no way to draw a resonance structure where we can get the double bond here. And so the meta sigma complex doesn't have this extra stabilizing resonance structure where everything has a complete octet. And so this is why the ortho and para positions are preferred when we have a alkoxy substituent.